Great. Okay. So on that note, David's connection is a little bit shaky, so I'm going to take over today for the introduction. So let me introduce today's speaker. We have Valeria Saggio here. She is a postdoc at the University of Vienna in Austria. She obtained her PhD at the University of Vienna under the supervision of Professor Philip Walter. Her research has a strong experimental focus on quantum computing with photonic platforms. She's worked on demonstrating efficient detection of multipartite entanglement in photonic cluster states. And she also works with applications of quantum mechanics to reinforcement learning. And her research includes bulk as well as integrated optics. And so on that note, with this very these very exciting research topics, I will hand the virtual floor over to you, and you can take it away.
Thank you. So I'm gonna share my screen. All right, so you can hopefully now see it, right? Yes.
Yes.
All right. So yeah, thanks a lot for the introduction, and I'm really happy about this invitation. So as you can see from the title, I'm going to talk about reinforcement learning and in general how it can be enhanced when quantum mechanics is used. All right, so I will start with some questions that then I will answer in my talk. So let's start. So I decided to keep this talk very basic because I don't know how many of you are familiar in general with reinforcement learning or with experimental quantum optics in general. So I hope it will be clear, but I really try to keep it basic. So we start from very fundamental questions. So in general, what's reinforcement learning? A few examples maybe, or where is it used? Then we'll see also what is the role of quantum mechanics, because we're talking about the quantum enhanced reinforcement learning protocol. Then we also see how we can then quantize reinforcement learning protocols. So let's see if quantum mechanics really brings a benefit to the field of reinforcement learning. Let's see what we have to quantize in the reinforcement learning frameworks. And then let's see also the experimental part. So in general, how can we implement them on quantum platforms? So I work with photons, so I will describe how we implemented a quantum reinforcement learning protocol on a photonic quantum platform. All right, so let's just get started. I will start, as I said, with a very basic introduction about reinforcement learning. And first of all, just to see where reinforcement learning lies. So let's see, we have the field, in general, the field of artificial intelligence, which is concerned with autonomous machines, algorithms that have to achieve some tasks that would normally require human experience or human knowledge. And so it can be, for example, mimicking some tasks or learning to achieve some goals. And so within the field, the general field of artificial intelligence, then there is machine learning. And machine learning is divided into 3 subclasses. So we have supervised learning, unsupervised learning, and reinforcement learning, which is what we are interested in. So I thought it would be nice just to give a very general overview also about supervised learning and unsupervised learning, just to really give an idea about machine learning in general. So we have supervised learning. A classical example of supervised learning is, for example, data classification. So distinguishing whether a certain image, for example, is the image or a cat or of a dog, for example. But of course, there's also other applications. So this is the first one. Then we have unsupervised learning, which is used to find patterns in data. So if you see, like, if you have a data set that looks like this, then the goal of an unsupervised learning agent would be to find, to find clusters in this data. And this is used a lot in companies to detect anomalies in data. And then the last thing, and this is the paradigm I'm going to focus on in my talk, is reinforcement learning. So reinforcement learning is a little bit different from the other two because it's based on an exchange of feedback between 2 entities, which are the agent and the environment. So I'm gonna now talk a little bit more in detail about this. So let's see. So in reinforcement learning, we have, as I said, two entities. We have an agent and an environment. So the agent is usually, I mean, you can see probably if you read some reinforcement learning papers, the agent is always usually sketched as a cute robot, but I mean, it can be like whatever has the ability of learning something. So it can be a robot, it can be an algorithm in general. It can be, so it's an entity that is provided with a goal that it has to accomplish. And then we have the environment. The environment is simply the world the agent plays in. And the agent can interact with this world because the agent sees the, let's say, the states of this world. And so the way reinforcement learning works is it comprises 3 steps. The first one is environment sends precepts, the so-called precepts, to the agent. So in this case, the precepts are basically the state. So we can say that the agent senses basically the state of the environment. And this triggers some action, some move in output. So let's assume that, for example, the goal of the agent is it has to find the exit of a maze, for example. So the action that the agent would make would be, for example, moving left or right or up or down to find the exit. So the action is just simply the move that the agent makes to try to accomplish the goal. And now the key point is whether, so now there should be an evaluation of whether the action was correct or not. So now let's say that the agent moves right in this maze and is able to find the exit. So it means in this case, the action was correct, the move was correct. And in this case, the environment would reward the agent. So it would give him a reward. If instead, for example, the agent moves left or up, whatever, and it does not find the exit, then it means no reward is given. But in general, these 3 steps are always repeated. Like it's always like this interaction like of precept, action, and reward or no reward that is sent to the agent. And the important thing is that every time a reward is sent to the agent, then this reward is used to increase the probability that the agent would perform well at the next round of interaction. So there is really a learning process in this, which is reinforced thanks to the presence of rewards. So the probability of then performing the correct action that led to a reward will then be increased thanks to the reward. And so in this way, by repeating these 3 steps, then at the end, the agent will learn to always output the correct action, so the correct move. So it will be, so at the end of the day, it will have learned to accomplish the task. So like this is really like the main idea. Of course, I mean it's very basic, but this is really like the main idea behind reinforcement learning. And now, just to maybe give you a more pragmatic idea of how it's used, or so let's see what a few examples of reinforcement learning can be. The very basic example, and is really what helped me a lot to also understand the framework, is, for example, a child learning how to walk. So in our case, in this case, the agent would be the kid who's trying to walk. So he's trying to accomplish the goal of walking. And then every time it falls down on the floor, it basically gets punished because it hurts himself. But then every time it manages to stand up, that it doesn't get hurt. So it basically gets a reward. And then in this sense, it learns in the end how to walk. So this is, for example, a very basic example of reinforcement learning. So reinforcement learning is also used in many fields. For example, in the healthcare domain, it's used to optimize, to find the right treatment policies, for example, for patients. Or it can also be used, for example, for news recommendations, like to recommend news to users to see what they like more and what they don't like. Or maybe this is what, I mean, I'm sure you heard of this. It's also used a lot in games, in computer games. And it's actually very interesting. I'm sure you heard of the AlphaGo. So this the game of AlphaGo, where reinforcement learning was used to beat human players. And but in that case, in the case of AlphaGo, it was a combination of supervised and of supervised learning and reinforcement learning. And then later on, another algorithm was developed, this AlphaZero, which uses reinforcement learning in the game of chess, Go, and so on. All right, this is like just a few examples of where reinforcement learning is used and can be used. But now the main point of my talk will be combining reinforcement learning with quantum mechanics. So now let's see what we can quantize and what it means to in general, like to have some quantum features in the reinforcement learning framework. So as I said, in reinforcement learning, we have two entities. We have an agent and we have an environment. And now what can happen is that we can, for example, keep the agent classical, but we can give some quantum features to the environment. So in this case, this is a classical quantum scenario. And this was used to design some quantum experiments. Actually, this is a very nice paper here. So this is, for example, one of the applications that this framework can offer. But then we can also now have the other way around. Now we can keep now the environment classical, but we can now quantize the agent. And so in this configuration, there is a very nice theoretical. This is a theoretical paper, and this paper is the experiment. Then it was the experimental demonstration. They did it with trapped ions. They basically demonstrated that it's possible to achieve a speed up in the agent's decision time. So what does it mean? It means that the agent can then decide on the next move to output faster. Okay, but in general, it cannot reduce the number of interactions that it needs with the environment. Right. And now the last part, which is also the focus of my talk, is where now both agent and environment are treated in a quantum way. In this case, it's possible then to demonstrate theoretically and experimentally. So this is what we achieved recently here in Vienna. So we demonstrated that it's possible now to achieve a speed up in the actual learning process of the agent. It means that the agent now can use less rounds of interactions with the environment to achieve the goal. All right, and this will be exactly the focus of this talk. But now the question is, so what does it mean that we quantize the agent or we quantize the environment? So what is quantum? So if you remember this slide here, where I explained how reinforcement learning works and the steps. Basically, the way, of course, I mean, this is very basic, right? I'm really like trying to really give a simple picture about this. So what happens in a quantum framework now is that precepts, actions, and rewards are promoted to quantum states. And what does this mean? It means that now, since they are quantum states, they can now be in arbitrary quantum superpositions. And now if you allow agent and environment to communicate using a quantum channel, then agent and environment can exchange these signals now in a quantum superposition. So the action is not just outputting a certain action, but it will be, the environment will have access to a quantum superposition of actions, for example. So this is the main idea behind this fully quantized reinforcement learning framework. And now let's see, again, just to give an intuition of why if we can prepare these superpositions of states, why we can then achieve a quantum speed up. This is really like just to give you the basic understanding behind this. So if we assume that the agent can output certain actions, you have, for example, action A1, A2, A3, AN, with a certain probability associated to each action. So we have P1, P2, P3, and so on. And let's assume that the correct action, that means the action that leads to a reward, is, for example, action A3. Right now, intuitively, let's say we want to play this classically. So classically, the agent just tries out what action he wants to output. So for example, it can output action 1, A1, A2, A3, and so on. If the agent outputs now action A3, which is the correct actions, then it means it will accomplish the goal. So it means the environment will send back a reward. And this reward will basically make the probability P3 associated to the correct action, it will make it bigger, such that at the next time it's more likely to output again this action, the correct action. And let's say that, I mean, so this is the very intuitive picture. And let's say that in this case, the agent learns after a certain number of rounds, x1, for example. What happens now if we use quantum mechanics? Then now the basic idea is, so if you see, basically, this is like the agent wants to find out of a set of n elements, it wants to find a certain element that is, for example, the correct one. And so in this sense, one can think of using a search algorithm, a quantum search algorithm, to find this action A3 faster. And this search algorithm is the Grover search. And so using this Grover search, then the agent can then reduce the number of rounds. So it can learn after a certain number x2 of rounds, which will be smaller than x1. And so this is exactly the key. This is also what I was saying before. The key of all of this is that the environment can access actions in a quantum superposition from the agent. And this allows basically the implementation of a Grover search protocol. Now, I would show basically the setup right now, but because I usually think that, that the Grover search is actually a very well-known algorithm. But to really understand the setup, it's also really necessary to really understand and recall how the Grover search works. So I thought of putting some slides, because it doesn't harm in general probably to recap again the Grover algorithm and see why you get the speed up. So I'm sorry for all of you who will probably get bored, because this is probably well known to most of you, but still it's for sure nice to have a look at it again. All right, so let's see more in detail about the Grover algorithm. So how does it work? Let's suppose that you have a set of n elements, x1, x2, xn. And let's assume that you want to find your target element, which is, for example, the element x2 in this set. And this element you identified with the win state. What you can also do is then, what you should do, this is necessary for the Grover search to be applicable. You have to create a quantum superposition of all the elements that you have. And so this is the initial state where you start from. And what you can also do, you can also write down the state orthogonal to the target element. So in this case, the state that is orthogonal to x2 is basically all the states but x2. So this state does not contain x2. And here you can identify this superposition here with the loose state, right? Because it contains all the states that you don't want to find. And so geometrically and very intuitively, you can also picture this. You can picture a plane. So you have the win state, which corresponds to the y-axis, and the loose state, which is along the x-axis, the x-axis. And then you have here an arbitrary initial state S, which is the superposition of all the elements. You can represent it as a vector on this plane. It forms a certain angle theta with the loose state, for example. And what you want to do, so the very intuitive idea beyond the Grover search is what you want to do. You want to then do some operations on your initial state to basically push it towards the win state. So you really want to try to rotate this as close as possible to the win state, because that's where you want to go. That's where you want to find. And this is exactly what the Grover search does. So if we see here, the Grover search is basically consists of two steps. The first one is the application of an oracle on initial state S. And as you can see here from this geometric picture, the effect of applying an oracle on the initial state S. This is basically the effect of flipping the state about the loose axis, so by the same angle theta. Okay, so we have this rotation, so we have this reflection about the loose axis. And mathematically, I mean, you need to do the calculations, but I mean, so I wrote it down here, so this is the outcome. So what happens is that the initial state, all the elements stay the same, except for the element x2, which gets a minus sign here. So the oracle basically has the task of identifying the target element. And this identification occurs by basically changing the sign of the target element of the x2. All right, so this is the first step. And now the first step, the second step is now applying what is called a reflection. This time it will be a reflection about the initial state S. So you can see here that now this state here is now reflected about the initial state S by an angle that is, of course, like 2 theta. Okay, you can see it here. And again, if you do the math, then what you can see is that this is the final output that you get. And so if you see it from here, that the amplitudes now of all the elements change, but you see that basically the amplitudes of all the elements have this value, except again for the amplitude of the element x2, which is again the target element, which is now this amplitude here. And this is bigger compared to all the other ones. So basically the effect of one Grover step is basically, so it has the effect of amplifying, of increasing the amplitude of this x2 element, such that then it will be, such that the algorithm can find it with a higher probability. And this is in general, this is seen as one Grover iteration. So you see that after one Grover iteration, I'm able to rotate the initial state, I rotate it towards the win state by a certain angle. But then of course, in general, this is not enough, right? Because we still want to get closer. And then what we do is we apply more Grover steps. So you have the first one, then you apply again oracle reflection again, and then again, until you really like get close enough to the win state. So you really try to maximize the overlap. So it means you try to maximize the winning probability. And then the important thing is that you should also, of course, not overplay it, because if you keep applying Grover, then what you do is you keep rotating, but then you start again, you start again to go farther away from the win state. You again decrease the winning probability. And then if you keep again applying the Grover search, then you start increasing it again because you again move towards this axis. So you really have these fluctuations in the winning probability. And for exactly for this reason, you want to find the optimal number of Grover steps that would maximize the winning probability here. So you would like to stop here around, like in this region. All right, and now the idea is, in general, exactly this point. So how many would you need to then find the winning state and then to stop? So you can see it here. If you assume you start with a certain state S, which has a certain angle, which forms a certain angle theta with the loose state, what you can do, you can impose that this theta plus a certain number k times 2. So for example, in this case, it's 3, right? You can impose that this is close to pi over 2 because you want to reach the winning state. So you want that this total angle is pi over 2. And then from here, what you can do, you can then extract this number k by doing some math and calculating this angle theta. So the important message here is that this is what you get. So you get that the number of rounds, the number of Grover steps that you need to apply to then find the win state is square root of n pi over 4. And this is exactly why you get a quadratic speed up in the Grover search. Because if you play classically, then you would have something in the order of n, but quantumly you get this square root of n advantage. All right, so this was the Grover step, just to give you an overview and the bigger picture. But now let's go back to reinforcement learning, and let's see how we can then apply this to our algorithm. So as a recap, again, as I said before, the agent can use this Grover algorithm to find the correct actions, so the winning states faster. And so now what we can do, we can now define the target element, which in this case corresponds to the correct action. We can identify it with the state, with the quantum state 1. Here, A stands for action. And then what we do, we take all the other elements, so all the other actions that lead to, that don't lead to the accomplishment of the goal, we just group them up using a zero state. Okay, so in general, we have basically the win and the lose state, which is what we have before. Basically now our elements are the actions that we want to find. And what we can do, as I explained already, we can prepare the initial state, which is a superposition of all the elements. You can see that as a superposition of the winning and the losing state. So you can prepare this superposition here, which corresponds to a certain vector in this plane. And now the idea is, how do we experimentally encode the states 1 and 0? Because we want to encode the 1 and 0 state, and we want to create the superposition, this initial superposition, because then we want to apply the Grover search. And so, as I said in the beginning, I work with photonic platforms. And as you can see here, basically, so this state S is a qubit, and it can be implemented using photons. So in general, how do we implement quantum superposition with photons? There's some ways. You can use polarizations, you can use there's different ways of doing this, but in these experiments, what we used was path encoding. And so if you see here, these white lines here represent some waveguides where the light can be coupled in, and this is a Mach-Zehnder interferometer. So you have here two bit splitters, they are fixed 50-50 splitting ratio, and this Mach-Zehnder interferometer is equipped with two tunable phases, theta and phi. And what you can achieve is, if you label, for example, the two inputs of your Mach-Zehnder with the quantum states 0 and 1, so that's how you label the waveguides. Then what you do is that when you tune this phase here inside, you can change the output distribution, the output of the Mach-Zehnder of your single photon. So if, for example, let's assume that you start from the 0 state, which corresponds to a photon entering this upper waveguide, then what you can do, you can, for example, implement an identity gate by setting this theta to a certain value that would still make you output the photon in the upper mode. Or you can also implement, for example, a swap gate. You set this theta to another value that now would swap the mode. And in general, what you do, so this is a video. I just think this is actually really cool. This is something that I took in the lab with an infrared camera. So this is exactly the shape that you can see. So you have this rectangle here is the Mach-Zehnder, and this is the light that was coupled into the waveguide. And here I was basically switching this phase theta to implement identity or swap, and then you can really see like the light swapping swapping at the output of the Mach-Zehnder. But in general, what you do, you can then, if you set this theta to some arbitrary value, then what you can achieve is a certain quantum superposition of your photon being in the upper mode or in the bottom mode. So in this way, you can then, this is how you implement basically a qubit using path encoding. And you can see here, this is an image of one beam splitter. So here, these lines here corresponds to these white lines. So they are the waveguides, and here you can see the shape of the Mach-Zehnder, and here you have the tunable phases. But now, so this is just one Mach Zehnder to implement a quantum gate. But in general, what we do, we have many of these. So in total, we have 88 of these Mach Zehners, which behave in the end as tunable beam splitters. And you can see here, like this is, for example, one unit here. This is another one, and so on. So we have them arranged in this configuration, and we have in total 26 of the input and output modes. And this chip is extremely small. This was designed at MIT. It's like 5 millimeters long, so it's extremely small, and it has a lot of components on it. All right, so this is the image of the chip, and now I'm gonna show how we implemented now this reinforcement learning protocol with this chip. So we didn't exploit the full chip. We just used the bottom part. So four special modes. And as you can see, now the agent and the environment are ideally assigned to some regions in the chip. And what is important here to have in mind is really like to pay attention to the labels here. So now we use one photon for this experiment, but we need to encode the actions. So the winning action here, the one state, and the losing action. So we use, if you see, for example, if you look at the middle, then you have these two waveguides corresponds to the lose action and to the win action. And so you can see that the way to prepare a superposition, this initial superposition that you need for the Grover search, is to use this U preparation to put the photon in a superposition of both this path, because in this way you create a superposition of 0 and 1 with a certain probability epsilon that you decide in the beginning. But then what you also see is that there's also another qubit that is used, which is this 0R and 1R, and this corresponds to the reward qubit, because we also need one qubit to encode the reward. And so what we do here is we use two unitaries here. They're basically two Hadamard gates to also then put the reward in a superposition. So again, if you follow, for example, the first two, then you see that these two correspond to these two special modes here, 1 and 0. So here now I put the reward in a superposition because the action qubit is still the same. And it happens the same here. Now I have again 0 and 1. And once I put the reward in a superposition, this is something that I need to implement then the oracle. And the oracle is implemented by the environment, which basically identifies, as I said before, the correct action. So as you can see here, again, this is exactly what I showed before. So now the effect of this unitary is now to flip the state, the initial state about the loose axis, and mathematically you have that the correct action gets a sign flip. And then the last step is to apply the reflection. So you need to undo basically the effect of these two unitaries here. So you have to go back to only having a superposition of actions. And now you can apply this reflection here. And so this is implemented out now by this unitary. And so in the end, the effect is that now at the end of the chip, the amplitude of the winning action will is increased. Okay, and this is something that of course does not happen in the classical case. In the classical case, I still have, the initial probability of finding the action. But then as soon as I play quantum and I play a Grover step, then I have an increased probability of finding my photon in the correct state. All right, so at the end of the chip, then the photons are coupled into single mode fibers and are sent to single photon detectors, D1 and D2. And now what the agent can do, it can now make a measurement and see where the photon is. So it destroys the superposition, and it will now find the photon in D1, which corresponds to the loose state with this probability, and the photon in D2 here with this other probability. The thing is that now the agent can make a measurement and can find where the photon is. But the thing is that the agent does not know whether now the state 0 and 1 of the action corresponds to, like, it doesn't know what they correspond to. So the agent needs a reward, as I said before, in order to learn. And in this case, whenever it makes a measurement, then it never gets any information about the reward, because here the spatial modes, so these two in the middle, they always corresponds to spatial modes 0 for both of them. Okay, so now, so the key point in this case is that the amplitude, the probability of finding the correct action is amplified, and this is what we get from the Grover search. But now we also need to get the reward in order to be able to make the agent learn. And so the reward is then obtained classically. So in the end, this is not really like a fully quantum configuration. It's a hybrid configuration, because now what can happen is that one can use the measured action as input in a classical round. So for example, if the photon was measured here in D1, then you can just test it again from this input, and then the photon will just go straight. And then this is associated with the 0 state reward, so there will be no reward. But instead, if the photon was detected in D2 in the previous slide, then the photon will be now input from the mode corresponding to D2, and then it will go down because now the environment here acts. So it will now be detected in D3, and here there is a reward because now this corresponds to the state 1. So now in this case, so now if the agent receives a reward, then it can then update the initial probability epsilon. So prepare a new superposition and then start a new round until the probability is maximized. And so this is exactly what I explained. So there is this quantum, so we call it like formally like epochs, but let's say, so this quantum round. So we have a quantum round to play a Grover search to amplify the probability of getting the winning state. And then we play a classical test round to get the reward. And then we keep alternating this. And this is what we find. So if we plot the average reward versus the number of rounds, then what we see is that this is the blue curve is this strategy that I'm showing you here. So you see that in the beginning, compared to just a simple classical strategy, which is this orange curve here, you see that here the blue curve like goes up. So you see that here it learns faster, and it achieves like a maximum here faster compared to the classical case. But then also what you see and what you don't want is that then it starts going down again. And it starts going down again because now if he keeps playing Grover, is what I showed before, that then it starts to overplay. So it reaches the maximum, and here it's where it should stop. But then it keeps playing because nobody tells him to stop. So then the probability starts decreasing again. And basically this is what you don't want to avoid. And so the trick to avoid this is to you play this alternation of quantum and classical only until you achieve this maximum, this peak that I showed. And then afterwards, you start to play only a classical strategy. So now you can see here in the screen curve, this is what I showed in the beginning. You have this growth here, which comes from the Grover plus classical test round. And then from this point on, then the agent starts just playing classically, and then it can go up like and increase. And yeah, this is the inset is a zoom of this part here. So basically what we want to, if we want now to quantify the learning time, then we need, of course, to consider only this region, like any probability within this region here, because this part is where we have the quantum advantage. And for example, if you choose a certain, this is arbitrary, so you can use a certain winning probability, for example, of 0.37. What you see is that if the agent plays using this Grover search, then it would need like 100 rounds achieve that probability. And instead, classically, we need 270. So in this case, yeah, you see that you have a reduction in the learning time when you compare it to the fully classical case. All right, so just to conclude now, just the take-home message is that it is possible if you want to run a reinforcement learning algorithm that would, where you want to really like reduce the number of interactions between the agent and environment, you can then create quantum states, and you should also allow the agent and environment to exchange these signals in quantum superpositions, because this is the key to enable the Grover search, to then find these correct actions faster. And so in the end, yeah, the main message is that it was proven that quantum technologies allow machines to speed up the learning process. And of course, this is only the beginning. And let's see, I'm really curious to see what the future brings, because now we're experiencing a lot of this progress. So we'll see. And thanks a lot. This was my last slide. I hope I was within my 45 minutes.
Thank you very much. This is exactly 45 minutes. This was a really great talk. So just to remind everyone, if you have questions, please just write the question or just write your name in the Q&A section, and I will promote you as a host so you can ask your question in person. While people are doing that, I had a quick question. So where you're comparing the classical and hybrid approach, it seems like with the hybrid approach, you have this very fast solution with the quantum approach. Then there's a plateau before the classical approach sort of kicks in. You know why that is? Why is there this sort of flat region where it takes some time for the classical algorithm to start optimizing again?
Yes, because what we do, so as I like showed here, we have, so in this, okay, so you're talking about this plateau basically, right? This.
Yes, exactly.
Yes. So this is because this probability here that I said, then you need to choose. So this is the switching probability, and I said this is the probability at which this strategy here is no longer advantageous. Okay, but basically what you see when you plot, if you do a plot basically versus the same plot but versus epsilon, what you see is that you have basically like the average reward increases, then it starts going down a little bit. But then at some point the classical strategy will then overcome it. So in the end, like it's not really at the peak that is the maximum strategy. Even if you overplay the Grover a bit, then you still have an advantage over the classical case. So you don't want to stop. You want to stop only as soon as the classical strategy gets better, and that's why you have this plateau there.
Okay.
Okay.
So I think we have some questions. We have a question from Alex Lasek and Thierry promoting. Alex, you should be a panelist now.
Yeah, I'm here. Hi, Valeria.
Hi.
Wanted to ask if you were able to put another qubit in that quantum first chip, could you just keep it all in there and not do the classical tests epoch, as you call it?
You
like
mean
is it just because you can't experimentally put the second qubit in there?
No. I mean, technically you could put another photon in the chip, but I mean the way the experiment is designed, even like with another photon, this would not help, because it's really like the way you define your spatial modes. In general, I mean, you could use other photons, but not to achieve this. You could use other photons to then increase the action space to then run more complex algorithms. That's an option, but not for this.
And then it scales in an obvious way. If your Hilbert space you search is like 16, how would you just then need enough qubits to have the same size of Hilbert space to count.
Exactly. I mean, then you would need the, for example, I mean, it's the usual advantage that you get from quantum computing. Yeah. So if you need to encode like, I don't know, 2 to the n, if you want to do n states, then you would need n qubits. Yeah.
Okay.
Section.
Okay, thanks.
All right, great. So let's go to Thierry Ferris.
Hi, thanks for the that was interesting. I probably have one or two questions, mostly on the technological part behind it. So the example I mean, at the beginning you gave some typical example where, for example, the child is walking and is learning like that. Okay. But that's I would still consider that as a fixed environment. So you know the parameters, and then when everything is fixed, you try to find a solution. Now, if you think about other technologies, for example, let's imagine a traffic flow in a city, for example, something like that, where actually the environment keep changing. So I can imagine that you can still have that kind of algorithm working, but no, or yes or no, or
no. Well, in our case, this is something that I didn't say, but in our case, yeah, it's a deterministic setting that is considered. So it means that basically every time the agent makes a move, then the reward always depends only on that, and also the next perception only depends only on that. So there is no. It's like, I mean, imagine like driving a car. If you steer left, then the car will only go left. There's no like small probability that the car will do nothing or go right. So in this sense, everything is fixed. That's what I'm saying. Yeah. So it's what you were saying before, like the environment behaves in a certain predetermined way, and this is what you have. You could then also consider like stochastic environments, where, for example, then there is a certain probability of assigning of giving a certain reward, because now the probability is, I mean, it's fixed because it's a deterministic settings. And so, yeah, you could probably then consider, yes, a quantum, like an operator that would implement that. Right. But yeah, this is not what we considered here.
Right, and the last question, well, second and last. So you mentioned the winning state, which is that's predetermined. But let's imagine that you simply don't have let's say you still have a winning state, but typically it has two parameters. For example, I still take the example of traffic in the city, where actually you want to minimize the number of cars, but you want to maximize the flow or whatever. Those kind of two parameters, and both are very important. So how could you deal with that? Could you still get the same scheme or something?
I mean, that would reduce probably to then having like more than one winning element in your protocol. I mean, sure, this is something that you can consider. It's probably not so easy like to consider it, although I mean, I didn't think about this, like to implement it with this setup.
So do you mean that maybe you have that kind of two rotations, you know, like rather than having a 2D map, you get a sort of 3D, so actually you have two problems and then try to.
Yeah, I mean, I guess you can have something like that, or I don't know, you can probably yeah, you can get something like that. I mean, you can really like trying to both like towards two goals at the same way, but this is like, it's not really obvious like to me. I mean, I guess I would have to think about it, but like how you would implement this like on this platform, right? I mean, it's a very generic thing that was implemented, and then yeah, if you want to work out the details, then
okay,
sure, you can probably do.
Thanks.
Okay, let's move on to Stefan, who had a question.
Yes, I really enjoyed your talk. Thank you very much. I have a little question on the film you showed. Can you explain a little more on what we were seeing in particular? What light
the video
you put in there?
You mean, yeah.
Yes, this is very nice. I really enjoyed that. But
yeah, yeah. So basically,
going in. I mean, my question, I guess, is what's going in. I mean, what is the light you put in? Because I guess we're really seeing directly, how to say, I'm really watching the electromagnetic radiation coming out, or what am I watching here?
Yeah, so you're watching basically the light that is coupled into the wave. So this is a waveguide, and I was really like coupling some laser light at a telecom wavelength inside, and then basically as soon as the light is coupled into the mode, then it excites the mode basically of the waveguide,
Yes.
and then you really see yeah, I mean so that's exactly what you see here.
This is classical light, right?
This is classical light because yeah, you would not see that with single photons.
No, you wouldn't see it, right?
But
Okay,
this is
okay,
no,
yeah.
I mean, and actually this video I took it just because we were having a lot of troubles coupling the light inside. I mean, usually we don't look at the chip with the camera, but like I don't remember really, like a lot of time trying to couple the light, and I thought, okay, no, something was clearly off. And then at some point you really just try with the camera, and then you see, like, as soon as you see something, then you know that you finally managed to couple. And then
Okay, well, thank you. Very nice. I have another little question, if I may. In the beginning, I enjoyed your introduction. I don't know anything about machine learning. But how different is reinforced learning from supervised learning? Because in some sense, I mean, the thing with the cats and the dogs, usually there is a database of pictures of cats and dogs. And so then in my mind, this is a little bit the same as reinforced learning, but I must be wrong on that.
okay, why do you say that? Okay, so if you consider, for example, supervised learning, you have a set, for example, images, and in the beginning, so you have some set of images that have some labels, right? Like this is a cat and this is a dog. So there is some training in the beginning that the machine uses to then understand if the next image is a cat or a dog. So it's really based on evaluation of data. It's based on a training on data that have labels. Okay, and instead reinforcement learning does not really use a data set in that sense. So it does not use some data, for example, images, and then the goal is to classify them. Like the goal is completely different. The goal is to achieve something through some interaction with an external world.
But in the training, when you use the word training, then the program is being changed so that the thing does better next time, right?
Yeah, sure. Yeah, this is also, yes, this is also true, of course, in supervised learning, right? I mean, you have this training in the beginning, and then in the end you get the right outcome. But supervised learning is really based on a set of data. And also the main difference also that I see is that since it's based on some training, so there's some human saying this is a cat and this is a dog, right? And then in this sense you can train the machine. If you try to do the same thing with reinforcement learning, which you could do, then you could never do better than the classical case, the human case, because there is a human saying, okay, this is this and this is that.
Okay.
So yeah, the best that you can achieve with reinforcement learning, with supervised learning is, okay, you achieve like at best human performance, but instead with supervised learning, since it's based on this constant rounds of interactions, you can also like play a game where you basically you make the agent self play the game, and in this case you can also explore some actions that the human would not explore, and in this case you could achieve superhuman performance. That's the main idea.
So to give the example with the kid, the parents are not there to applaud. It's just the environment. Is that what you're saying? Because the reward, the example with the kid, one of the ways the kid learns is the parents are all happy, right? Because they start applauding. They're jumping.
No, I think no. So in that case, no, the parents no. So the environment is everything that is around the kid. So the floor, for example,
yes, yeah. And
the percept is what the kid sees, so what the kid perceives, and then the reward is basically the kid not hurting itself.
Okay.
That's the.
Yeah. Okay. Thank you.
Sure.
All right, thanks. We have time for a few more questions, so let me just get Adam to ask his question, and then I think David had a few, and that should be...
Hello, thank you for the talk. First, it was very interesting. I just had a question, maybe it's more about Grover algorithm. I don't really understand how you implement the oracle, for example. how you flip the x2 qubit in your example, as you don't really know at first, from what I understood, which state is the winning state. I mean, when you do the algorithm, you don't know which action you have to do to have a reward at first. So
yes. So if you consider here, so you start here when you prepare the superposition, right? Yes. So the agent does not know which action is the correct one. So then it just prepares a superposition of both of them, and then this environment is built such that only if the photon is here in the bottom mode, so corresponding to the correct state, then this gets a reward. So the environment knows what to give the reward to.
But I mean, the environment knows, but at some point the experimenter has to implement the device, so he has to create some quantum gates to implement the algorithm. So
yeah, sure. But so what do you mean? So these quantum gates is what we said in the beginning. So the goal is I input some light in the chip and I say, I want this light at a specific output in my chip. Okay, but I just said this, I said it to be random in the beginning. And then I set the gates in the beginning and then I let the chip play by itself. That's the main idea. And then in the end, I will find the photon where I want. So of course, I know where I want to go. But yeah.
Thank you.
Sure.
All right, David, does your microphone work?
Can you hear me?
Yes.
Yes.
Okay, so let's see if I can go live with my questions. There are two questions. The first, they're both like what's next type questions. So I guess maybe what you will be saying in your postdoc interviews now in the in the future. But so the first question is basically what's next in terms of quantum technology? I mean, these chips that you're working on, they're pretty much the coolest thing I've seen so far in quantum optics. But what's the kind of next step? Are people developing nonlinear versions of these chips, or what do you think about that? And then the second question is kind of what's next in terms of quantum reinforcement learning. So you use this very clever way of putting Grover's algorithm to play, and you get the square root of n improvement. Is there any hope of getting a better than square root of n improvement in like a general setting? Like, could you get a better improvement if the kind of feedback from the detectors to the agent was a quantum one? I guess you get my question. Yeah, those are the two things.
Okay, so I start with the first one. So what I see in the future. So the next step in terms of integrated optics is trying really like to increase the number of waveguides, because in that case, and the number of components in the chip. So I know that now, I mean, groups are trying to push to really like get to like 100, at least 100 like of optical modes to have a fully connected configuration. And in general, I mean, they're probably pushing to go even to more than 100. Of course, I mean, I imagine with some difficulties. And then the main idea, because in general, I mean, optics, I like to work with photons, but I mean, of course, bulk optics is not scalable, right? So I mean, the way to go, if you want to do quantum computation with photons, you need to use integrated optics. And so the main idea is now also to, I mean, there's groups who put now also sources inside the chip and detectors at the end, so such that they really have like just one chip where they just shine some laser light inside, and then they do like photon generation, computation, detection, like all inside the chip, which is super cool. But so yeah, so the next step is definitely like trying to increase the number of waveguides, and also to try to keep the losses at a minimum, because that's a big problem that I see. But I mean, of course, there's also like, this is a silicon on insulator platform, but there's also like different types of platforms that try to then maybe like have the chip that is a little bit bigger, but then they try to reduce the losses. Okay, and then the second question in terms of reinforcement learning. So yes, there's some other ideas that would go beyond, that would perform better than the quadratic speed up. For example, it depends, like if you can change the oracle and the general problem to achieve a different type of speed up. For example, if you use the Simon's problem, there is a theoretical paper where they demonstrated that then in that case, you can achieve an exponential speed up, for example. Or if you use a recursive Fourier sampling, then you can achieve some super polynomial speed up. But I guess what I see in this sense is that this type of scenario is still kind of artificial in some sense. I didn't talk about the details, but there's some strong assumptions that you need to do in order to be able to quantize this environment, right? And if you want to really get closer to more like real problems, like let's say, for example, if you want to implement even the simple grid word problem, for that you will need a little bit of more effort. I mean, I would need really to go into this because this is something that I did not show, but I mean, there's still like something to do in order like to really like get closer to some really like real life examples and trying to relax all these strict assumptions that you still need to quantize these algorithms. So that's probably the next step.
Super interesting to hear about. Maybe then like in a year's time, we can have you back and talk about the next steps.
Hopefully, let's see.
Yeah.
Sure.
All right, thank you very much for this talk. I think that's it for the questions, and that's it for time as well. So yeah, again, this was a great talk. Thank you for coming.